Hello viewers, welcome once again to another edition of Subject Math. Today we will be solving past questions on radioactivity. And the first example we have says, a sample of radioactive substance has a half-life of 35 days. Calculate the fraction of the original quantity that will remain after 105 days. Okay, so the first thing we need to do is to write out our parameters. The capital T is the half-life, which is 35 days. The small t is the time taken, which is 105 days. So from this question, we are asked to calculate the fraction of the original quantity remaining, the fraction remaining. And from our formula, if you watch the previous video, fraction remaining is equal to 1 over half. So we have TT and we don't have our R. To get our R, we use this formula. N is equal to, there's a formula connecting T and T, which is equal to this. And that gives us 35. And this will give us 3. R is equal to 2 raised to power n, which equals to 2 raised to power 3, and that will give us 8. Now, coming back to the fraction remaining, this formula, to calculate the fraction remaining, we have 1 over r, which equals to 1 over 8. You can see that it's very, very simple. The question here says, uranium of atomic number 92 and mass number 238 emit an alpha particle from its nucleus. The new nucleus formed has respectively atomic number and mass number. So we are looking for the atomic number and the new mass number. So let's just write out this. Uranium, the mass number is the number of 238, while 92 is the proton number. Emits an alpha particle. Alpha particle is 42 helium. So the question says that, what's the atomic number of the new element formed? So new element formed is 238 minus 4, that will give us 234. And then 92 minus 2 will give us 90. So the atomic number is equal to 234. The mass number is equal to 234 and the atomic number is equal to 90. So I want to believe that is very explanatory. The third question here says, if the decay constant of a radioactive substance is 0.231 per second, what is the half-life? This is a very straightforward question. You recall that half-life is equal to 0.693 over decay constant. So this is the formula connecting them. So we go ahead and write this. Our decay constant is 0.231. So therefore, our T is equal to 3. So the half-life here is 3 hours. The fourth question here says, the half-life of a radioactive substance is 3 years. 3 years half-life. How long in years will it take 384 of the substance to decay to a mass of 6 grams? So we have the initial mass of the substance to be 384 grams, and we have N2 to be 6 grams. So we are asked to find how long it will take, how many years it will take the substance. So you recall that 1 over R is equals to N2 over N1. So from there we have our N2 is 6, N1 is 384, and that will give us 6L1, here 64. That will give us 1 over 64. So we have 1 over R is equals to 1 over 64. And let's not forget that, okay, so from here, R is equals to 64. So let's not forget that 2 raised to power n is equals to 2 raised to power 6. And that will give us n is equals to 6. So please, let's not, what I did here was to recall the formula that says R is equals to 2 raised to power n. So let's not forget that. So now that we have n is equals to 6, we can just put that into this formula. N is equals to T over T. There's a formula connecting these two T's. I mean the half-life and the time that we are actually looking for. So since we have our n and half-life, we go ahead and multiply our capital T, which is the half-life, is 3. So we have 18 years. You can see that that is very, very simple. The 5th question here is very similar to the one we did earlier. The half-life of a radioactive substance is 5 hours. So we have our T to be 5 hours. If 5 grams of the substance is left, that should be our N2, because that's the mass left. So our N2 is equals to 5 grams. After 20 hours, the time taken, that's 20 hours, determine the original mass, that's N1. So from here we are asked to find our N1. So we just go ahead and recall this formula that says N is equals to T over T. We have 20 over 5, which equals to 4. Which equals to 4. 20 over 5, which equals to 4. And I hope you can also recall that R equals to 2 raised to power n, and that will give us 2 raised to power 4, which equals to 2 in 4 places. 2 times 2, 4 times 2, 8 times 2, 16. And that is 16. Our R from there is 16. So if we put it into this formula, there's a formula, if you recall from our previous video on radioactivity, where all these formulas were being introduced, you recall that N2 over N1 is equals to 1 over R. So we have our N2 to be 5, our N1 is unknown, 1 over R is 16. So by the time we cross multiply, the N1 is 16 times 5, and that will give us 80 grams. So this answers the question. The original mass of the substance is equals to 80 grams. I believe that is very explanatory. Okay, so the next question here says, a nucleus has a proton number of 84. It emits an alpha particle and a beta particle to achieve stability. What's the proton number of the product? Okay, so let's assume that this is the nucleus. It has a proton number of 84. The proton number is a number down. We are not given the mass number. And we are told that it emits an alpha particle. Alpha particle is 42 million. And it also emits a beta particle. Beta particle is 0 minus 1. Then we have, what's the proton number of the product? So the product, let's assume our product is um, we have used X. Let's say we have Y. I'm just assuming that the element, the new nucleus is Y. So we have 2 minus 1, that will give us 1. Subtract 1 from 84, that will give us 53. So the new proton number is equals to 83. I want to believe that is very clear. To the next question, we have this sodium plus proton to give us this. Now we are asked to find P, Q. What are the values of P and Q? So the solution to this, we are asked to find P, we are asked to find Q. I have 23, 11, and I have this, plus proton. Proton means 1 mass number and 1 atomic number. So this is the proton. To give us PQ, X plus alpha particle is 42 billion. So let's go ahead. 23 plus 1 will give us 24. 23 plus 1 here will give us 24. 4 plus P. So our P from here will be 24 minus 4, which equals to 20. Which equals to 20. So our P here is 20. Likewise, 11 plus 1 will give us 12. 12 minus 2 will give us our Q. So Q is equals to 11 plus 1, which is 12 minus 2. And that will give us 10. So from here, our P is 20 and our Q is 10. I want to believe that is also very, very explanatory. Another example we have here says deuteron and tritium fused to form a helium nucleus according to this equation. Calculate in joules, take note, the energy released. So we are asked to calculate the energy released in joules. So what do? We need to calculate the mass of this side, which is the reactant, then the mass of this other side, which is the product. Then we find the difference in the masses. So that's all we need to do. So we go ahead to find the mass of the reactant. Mass of reactant, which equals to the mass of this plus the mass of this. I will be given. We have 2 point mass of reactant, which is 2131 each. Their masses is equals to, we have 2.014 plus 31 each. That's 0.0160. Now, addition of this will give me 5.03015. So we go ahead and do that of the product. Here is the product. We have 42 helium plus 1 O. So what we are looking for is the N. 42 helium has been given as this, which equals to 4.00260 plus, I have this 1.00867. Now, addition of these two is going to give me 5.01127. Don't forget, I told you that the mass defect is the difference between the product and the reactant. So the mass defect is equal to 5.03015 minus this 5.01127. and that will give me 0.01888. Now, if you look at it, we need to convert it from AME to electron volts. And to do that, the energy released, we multiply by 931. They said F1U is equal to 931 MeV. So we have energy release equals 0.01888 times 931 MeV. So by the time I multiply that, I have 17.57728. Don't forget, this is 10 raised to power 6. This N here stands for 10 raised to power 6. So if we are converting this to joules now, 1 electron volt is 1.6 times 10 raised to power minus 19. So if we convert this, to joules, we have 17.57728. I told you that this is 10 raised to power 6 times 1.6 times 10 raised to power minus 19, which is 1 electron volt. And that will give me 2.812 times 10 raised to power minus 12 joules. So the energy released in joules is given as 2.812 times 10 raised to power minus 12 joules. Our last example for today says, calculate in joules the binding energy for lithium 73, which has an atomic mass of this, the mass of neutron, mass of proton, AMU, and 1 electron volt is given as that. Okay. So from here, the number of proton is 3, and the number of neutron is 4. That's 7 minus 3 is going to give us 4. So to calculate the mass of proton, number of proton is equal to 3. Number of neutron is equal to 4. How did I get that? 7 minus 3 will give me 4. Okay. So to get the mass of the proton, I'm going to multiply 3 by this. 3 times this, and that gives me 3.0234. Then I go ahead to find the mass of the neutron. We said it's 4, that's 4 times, this is the mass of neutron. So I have 4 times 1.008677, and that will give me 4.03468. Okay. We have already been given the atomic mass of lithium to be 7.01. So we need to look out for the change in mass. First, let's add together the mass of the proton and neutron. So mass of proton and neutron is equal to 3.02349. Okay. So we are adding the mass of proton plus neutron. That's 3.02349 plus 4.03468. So addition of that gives me 7.05. So I have the 7.05817. So to find the mass defect, that's the difference in mass between when we have proton and neutron and then the atomic mass of lithium. That will be 0.817 minus this 7.01600 U. And that will give me 0.04217 U. So we need to change from that to electron volts. Don't forget that 1 AMB is equal to 931 micro electron volts. So what that means is that 1 U is equal to 931 MeV. So this we have 0.0421 times 931 times this M stands for mega, that's 10 raised to the power 6 eV. So by the time we multiply that, that will give me 39.26027 electron volts. 39.26027 electron volts to joules. You recall that 1 electron volt is equal to 1.6 times 10 raised to the power minus 19 joule. So we just go ahead and multiply 39.26027 times 1.6 times 10 raised to the minus 19 joules. So if you multiply that, we are going to have 6.28 times 10 raised to the power minus 12 joules. I want to believe that this is very, very clear and explanatory. Please and please don't forget to subscribe to this channel. And in case you need clarity on the formulas to solve questions on radioactivity, you go back and watch our previous video on radioactivity. Thanks for watching.